All right, everybody, we have now completed going over the 5 rules of factoring. And now we're going to put all that information together. Today we're going to talk about factoring completely. Factoring completely means to break down the polynomial expression into multiplication as far as you can go. When we factor completely, it means we may not just use one rule of factoring. We may incorporate 2 or 3 rules. So recall, there are 5 rules of factoring we've just learned how to use. We've learned GCF, difference of perfect squares, trinomials, grouping, sum or difference of perfect cubes. Okay? What's going to happen is I'm going to give you an algebra expression and I'm going to say factor it completely. I want you to break it down as far as it can go. Now, how does this relate to real life? Well, let's think. Suppose you come home from work and you get in the kitchen and you see this wonderful, gooey chocolate cake sitting on the table. The icing is just melting because the cake just come out of the oven. You could smell it. The chocolate is just filling the room. So you go get yourself a glass of milk. You sit down, you cut yourself a big piece of this cake. And you take a bite, and oh my, you spit it out. Because even though it looks beautiful, it doesn't taste right. Because somebody forgot to put the sugar in. They forgot an ingredient. Realize that a recipe is breaking down into little pieces what makes the whole cake, right? Well, that's what factoring is. We have a polynomial expression, and I want to break it down into its little pieces that are connected by multiplication. So we want to break it down as far as we can go. We want to make sure we list all the ingredients. Okay, so if you look at your PowerPoint, here's my expression I want to factor. 2x squared minus 50. So the first thing I look at is I say, okay, the first rule of factoring we always try to do is GCF. It doesn't matter if we have 2 terms, 3 terms, 4 terms, 5 terms, 8 terms. Every time you're asked to factor, the first rule you look for is GCF. If your terms have something in common, a term in common that you could factor out, you need to do that first. That's why it's listed as rule number 1. So if we look at 2x squared and 50, it's obvious they are both even numbers. We can divide them by 2. So our GCF is 2. So we're going to pull out that 2 and put 1 parenthesis to say what's left. Remember, when we do the GCF rule, there's only 1 set of parentheses. So I put the GCF 2 in front, and then I do my division. 2x squared divided by 2 would be x squared. Negative 50 divided by 2 would be negative 25. So when I write this in factored form, this expression, I have the 2 in the front and then the parentheses x squared minus 25. Now, here's the problem. Are you done factoring or can you use another rule? Well, if you look inside the parentheses, you have x squared minus 25. You have 2 terms. So when you go to that list, you've already done GCF, so you're done with that rule. What rule of factoring have to do with just 2 terms? Well, there's 2 rules. In spot 2, there's difference of perfect squares, and that's why I have it in spot 2, because it has 2 terms. The other rule of factoring that's with 2 terms of binomial is sum or difference of perfect cubes. Now, I know I have that in spot 5, but we've already discussed that. It's down there because it's the rule that's used the least. So when I see 2 terms, this is what I'm going to do. I'm going to say, first, is it a difference of perfect squares? Well, let's look at our vocabulary. Difference means subtraction. Okay, I got a subtraction symbol. Perfect square means a term times itself. For a variable to be a perfect square, it has to have an even exponent. Well, we have x squared. The exponent's even. For a number to be a perfect square, it has to be off our list. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and etc. 25 is on the list. So now we know inside that parentheses, that is the rule, difference of perfect squares. So now I have memorized. Okay, if I'm going to factor using difference of perfect squares, I'm going to put 2 sets of parentheses because difference of perfect squares always factors into 2 binomials that are conjugates of each other. And the way I get those binomials is I just think backwards. What times itself makes each of those terms? So what times itself makes x squared? That's easy, x times x. What times itself makes 25? That's easy, 5 times 5. Because there's a minus sign, a difference sign, you know the signs in those binomials have to be opposite. One has to be a plus, one has to be a minus. That's why those binomials are conjugates of each other. Now, when you write your answer in factored form, remember, you've already pulled out that GCF of 2. Don't forget about it, or you'll get marked wrong. You can't lose your ingredients. So you bring down the 2. We're not going to write x squared minus 25 anymore because we just broke that down to be x plus 5 and x minus 5. Are we done? Well, let's look inside our parentheses. We have an x plus 5. It's a binomial. Well, that can't be a difference of perfect squares because it doesn't have a subtraction sign. So it has a plus, so my only option is to say, is it a sum of perfect cubes? Well, it's a plus, it's a sum, but x is not a perfect cube because to be a perfect cube, your variable has to have an exponent that's a multiple of 3. And 5 is not a perfect cube because if you know your perfect cube list, 1, 8, 27, 5 is not there. That tells me that binomial is in lowest terms. We leave it. I go to the next set of parentheses, x minus 5. Again, I only have 2 terms. So I'm looking at the rules difference of perfect squares or difference of perfect cubes. It has a difference sign. Is it a perfect square? Nope. X is not a perfect square because it doesn't have an even exponent. 5 is not a perfect square because it's not on our list. 1, 4, 9. It's not there. Is it a difference of perfect cubes? Nope. X is not a perfect cube because you would have to have an exponent that's a multiple of 3. 5 is not a perfect cube because it's not on the perfect cube list. So that tells me that parenthesis, that binomial's in lowest terms. And once I check that and say, okay, there's no more rule I can apply, I am done. In this expression, I never looked at the trinomial rule because I never had 3 terms, and I never looked at the grouping rule because I never had 4 terms. That is why that checklist is important that you memorize it in that order. All right, let's go to the whiteboard and try some examples of factoring completely.